Okay, welcome back. Hope you were able to complete Lab 3 without any issue. Health check should have discovered that VLAN was invalid in our environment, and you should have been able to rectify that, remediate, and now have a backup of your distributed switch in a known good working state. We'll need that backup in lab number 4, which we'll do after not this lesson, but the lesson coming up after that. So in any case, welcome to this lesson, the lesson that is about a really powerful feature called Distributed Switch Network I/O Control. Not a new feature at all. It's been around since the vSphere 4.1 timeframe. In fact, it was first introduced back then. It was then updated to version 2 with vSphere 5.1, and then with vSphere 6 introduced Network I/O Control version 3. So let's take a look at what this entails, because lesson 3 or version 3 is actually very, very powerful and quite significant. So, and also worth noting, it's already enabled by default. So what is it, right? Your goal here is to understand and to be able to describe Network I/O Control and how it enhances overall performance. Describe how to use Network I/O Control to allocate bandwidth to different types of system traffic, and to be able to describe how to use Network I/O Control to allocate bandwidth to VMs. To basically put it simply, the goal of Network I/O Control is you've got a whole variety of networking traffic coming in and out of your distributed switch. This is going to create an equalized access as a default configuration. So here we go. Right? Understanding what Network I/O Control is and what it does. Now, what we're showing in this particular example is basically Network I/O Control in a nutshell. Doesn't really matter which version. We are referring to version 3 here on the slide, but to place it quite simply, right? You can use Network I/O Control to allocate network bandwidth to business critical applications and resolve situations where several types of traffic compete for common resources. So what does that mean? Well, what we see in our picture, we've got an environment where every host has 2 network adapters. That would be a standard at least, right? You need redundancy. And by the way, if those are 2 10 gig adapters, you have 20 gigabit of aggregate bandwidth. If those are 2 25 gig adapters, well, then you got 50 gigs of aggregate bandwidth. If they're 40 gigs, well, obviously you got 80 gigs of aggregate. And then if they're 100 gig adapters, well, there you go. You got 200 gigs of aggregate bandwidth. So what we're first of all achieving is a large pipe, right? A large networking pipe with a lot of bandwidth. Then what you'll end up putting in this distributed switch is probably a lot of different kinds of traffic, right? So that's really the goal here, to simplify administration here by adding all of your networking services into one bucket of networking I/O. Now, if they're all competing for bandwidth, how do we ensure every type of traffic gets their appropriate share of that bandwidth? And right out of the box, by default, every type of traffic, these aren't necessarily port groups, these are actually the different types of traffic services that are typically set up in a vSphere environment. You might have your VM traffic, of course, management traffic, vMotion traffic, storage traffic, could be iSCSI, it could be NFS, it could be your replication traffic. You've got all kinds of traffic that is going to potentially pass through this large networking I/O channel that you've set up with an aggregate levels of bandwidth. Right? And so by default, in fact, every type of traffic has the same share setting, right? When it comes to setting up Network I/O Control, what we're doing is we're allocating network bandwidth using network resource pools that are going to be set up with your typical types of resource allocation settings. When it comes to networking I/O Control, you can set shares, you can set reservations, and you can set limits, just like you can when it comes to CPU and memory and other networking and other types of resources. So this is giving you the same types of resource allocation configurations for our network. So by default, all these types of traffic all have, in fact, the same share value. So therefore, when there's contention for the bandwidth, every type of traffic gets their fair share of that bandwidth, with one exception. Virtual machines, by default, get double the share setting, which I guess makes sense. VMs are a pretty critical part of any environment. So VMs will by default get twice the priority for network bandwidth when there's contention for that bandwidth. Now, how we set shares in a distributed switch, it's a much different set of numbers compared to setting shares for, say, CPU and for memory, where they're like in the thousands, right? 1,000 CPU shares, or for instance, is a kind of a standard thing. Well, when it comes to networking shares, it's basically between 1 share and 100. So between 1 and 100, and all the types of traffic by default get 50 shares, except VMs by default get 100 shares. Hence how we see that we have double priority for our VM traffic. But if we want to set other things, right, we want to set possibly minimum requirements, right, set a reservation for our types of traffic so that not only do we have a priority to compete, that's shares, right, you get a priority based on, your priority is going to be determine how you compete with other services when there's contention, but a reservation guarantees that bandwidth. So we can reserve bandwidth for system traffic. We can also apply a limit to set an upper bound for how much traffic that a type of traffic can utilize. And we have very detailed levels of access control for our resource management. Now, how you set this is actually kind of interesting. If you are familiar with how we do CPU and memory resource pools, we also have a concept in our network out control called a network resource pool. And if you know your CPU and memory resource pools, you have this hierarchical resource management for CPU and for memory. Well, we do the same kind of thing for networking. How we see this is you have really the root resource pool, the actual hardware level of the resource, and then you can create network resource pools that draw from that. Just like how you can create a CPU or memory resource pool based off your ESX server's root pool of CPU and memory. So let's think about it. What's in a root pool of an ESX, the root pool of a networking card? The root pool of a networking card is basically whatever its bandwidth is. If you have a 10 gig networking card, that is your root pool. You can then define how much of that is going to be guaranteed to different kinds of traffic. So on your 10 gig, if those are your adapter speeds, or if you have a 40 gig adapter, that's your networking speed, you can specify what portion of that adapter's bandwidth is going to be made available for other types of traffic. So this is what we call the bandwidth allocation model for system traffic. What we'll do is at the network adapter level, you're going to assign a share value, right? But that's already set by default, but you can always adjust this. You set the share value for how the different types of traffic are going to compete for the resources on each and every networking adapter. That share value will be between 1 and 100. As we said, every type of traffic by default gets 50 shares. VMs get 100 shares. But you can also define a reservation as well as a limit on each and every network adapter. Now, when you set these, you're setting the same setting across every single network adapter. You're basically defining how much of a portion of each of the network adapters is going to be guaranteed for management traffic, how much is going to be guaranteed for VM traffic, how much is going to be guaranteed for vMotion traffic, and so on. You do this by clicking on your distributed switch into its management configure page, right? Click on the configure tab, and then notice down under the resource allocation section, there's two sections. There's system traffic, and then there's network resource pools. Well, basically, we're going to create network resource pools for our VMs to set up, how much we want to guarantee for our VM traffic. But before we create a network resource pool, we do need to guarantee a certain amount of bandwidth for our VM traffic. And while we're doing all that, we can set a certain amount of bandwidth for all of our other types of traffic. So notice here, if you edit the system traffic settings page, what you're seeing here, in fact, is actually two big parts of this interface. When you click on the system traffic page, what you'll find is on the bottom portion of this page is all the different types of traffic out there. There's management traffic, fault tolerant traffic, vMotion traffic, VM traffic, and so on. When you'll note here, they will all have their share value defined as a default. They all have 50 shares by default, except VMs get 100, but none of those types of traffic have anything guaranteed to them. Clicking on edit will then let you adjust, say, for instance, management traffic, where we're going to set, in this case, a 500 megabit reservation for our management traffic. So whenever any type of management traffic hits any network adapter, 500 megabits is guaranteed for management. It's basically giving it something a little bit more than what it can compete for, right? It's competing with its share value, but before it even has to compete, it's already got 500 megabit guaranteed. You'll also notice that the max reservation is 7.5 gigabit. Well, what does that mean? Well, back over here in the main panel, you'll notice here that we have 10 gigabits of available bandwidth that we could potentially reserve. That's 10 gigs because the minimum speed of any one of our adapters is 10 gigs. It's always using that minimum speed as a way to determine our baseline for defining these things called system reservations. And the policy, or I should say the design of reservations, max at 75%. So whatever your bandwidth is, in our case it's 10 gigs, the most we could ever reserve is 7.5 gigabit. We're only allowed to reserve 75% of any adapter's total bandwidth capabilities. And this is just so that we can't just reserve the full capacity of the adapters. There's always going to be a little extra wiggle room of 25% that you have available that cannot be reserved. And then once you've actually selected OK over here, you'll find that this will show that we've now reserved 500 megs out of our 10 gigs, with the most that we could reserve is 75%. So what we'll do here, we'll take a quick break, let you absorb all this, and we're going to talk about how you actually see this, follow along a few different examples of how we go ahead and use this as a way to get started for defining our network resource pool. So go ahead, we're going to take a quick break, and we'll come back and dive a little bit deeper into this.